Swayam Prabha. Digital India. Educated India.
Okay, hello everyone, welcome back. So in the last couple of lectures we talked about how the photon interacts with the cavity and so on, right? The last thing I want to cover in the area of nanophotonics is nanofabrication, because we have always been talking about these nanostructures, but we never really told you how to fabricate these nanostructures. Okay, so I thought I'll spend half an hour to 45 minutes or so in this, and then we will try to tie up that last bit that we have not addressed so far. Okay, so in this direction, what I wanted to do is, let's say we have shown this first negative index material that was created. I told you that this was fabricated in 2001, and it consisted of this split ring resonators, and we told you that there are these metals which are copper, right? The split ring resonator is essentially copper here. Copper. Split ring resonators, SRRs, split ring resonators. How do we fabricate these structures? Okay, so the process is, we use a PCB, so it's a traditional, we can actually get it done anywhere. I mean, these are very widely available processes because these structures are relatively large. In RF frequency, the structures are relatively large in the scale of millimeters. Okay, so but what I'll do is I'll quickly, try to go through the process of how it is done so that you get an idea of how these things are fabricated, and then I'll tell you how to make them smaller. So that will be the goal of this lecture. All right. So to start with, let's say you have this substrate containing a copper film. That's what we buy. I mean, we call this as a PCB laminate. Let's say PCB laminate will be a substrate. In this case, that will be some kind of mostly FR4 substrate coated with a copper film like this. Okay. So now we want to pattern it. Can we simply, one of the ways to do that will be simply to, wherever you want, you keep the copper film, everywhere else you have to remove. That's what finally we have to do, right? So if it was something like, machine level thing, I'll simply scratch away some things, right? That's how I can do. One way of doing it is by scratching away, right? Or etching away the copper from areas I don't want. Okay, how do we do that? We want it to be very, very precise. So we go through a process which is known as, a sequence of steps, lithography followed by etching. Okay. So this will be fabricated by lithography first. Lithography means basically writing on a, litho means stone, lithography is writing on stone. I mean, it's in a kind of making a pattern first, and then after that followed by plus etching copper. First you try to make a pattern and then etch away. How do we do that? So first step is basically to apply what is known as a photoresist. Okay, a photoresist is simply a photosensitive material. For example, there are multiple types of materials. I can take a thin film of organic compounds and I can shine high energy photons on that. What are high energy photons? In this case, you can have something like UV photons. Okay, when you have UV photons, the energy is something like 3 eV or so. Because of the high energy, when you shine it on an organic molecule, the bonds will break. Okay, that is something similar to what you would see even in the case of, let's say, people tell you that, okay, don't go out in sun, UV radiation is harmful to skin, it causes cancer. Why does it cause? Because the UV radiation can actually break the bond. The bonds that are there on the skin, they're organic bonds, and the bonds have bond energies in the scale of 1 to 2 eV or something like that. When an UV photon hits that, it can actually break the bond. When the bond is broken, the skin is getting damaged. So that's why we don't like that. Okay. So in this case, we actually want the bonds to break. Okay. So we can expose this photoresist to the UV radiation. So a photoresist will be, one of the famous examples will be like, a long chain, organic molecules which are in form of long chain. When you hit a UV photon, the chains will break. Okay. And so when the chains break, the material becomes easily soluble. Okay. So that is the process. So now what we will do is, if I just simply coat a film like this, if I take a substrate and a copper, just the color, this is copper film, right? If I apply a photoresist and simply shine the photons on this, is it okay? It will not. The reason is, if you apply photons everywhere, all the regions, basically the chains will break and the photoresist will become easily dissolvable. That is not what we want. We want to selectively expose certain regions only. Where we want to etch, we want to expose so that we can remove the photoresist from there and then we can etch. Okay, and that is what we do in this case here. So for example, here the third case, you first step is prepare substrate and then you apply a photoresist and then expose to UV light. So you create what is known as a mask. A mask is simply, if I take a transparent film and I put, let's say, a pattern I can write on that and I can make it block light, right? A mask is simply masking certain regions of light from passing through certain regions. So in this case here, what we have is basically glass coated with chrome. This black region here is chrome. So chrome is basically, if I take a 100 nanometer chrome film, will it transmit light? We understand that it won't transmit. We have calculated the transmission coefficient. So wherever you have the chrome film, you will not transmit light. Wherever you don't have the chrome film, you can actually transmit light. So when the UV light hits this particular region here, it becomes, exposed region, right? This is my exposed PR, which is basically easily dissolvable. Okay, so basically that's why I showed it in a slightly different color. So when you have photoresist like this, so you have this PR. Right now nothing much, still the film is there. Now take that film and put it into what is known as a developer solution. A developer is something that will basically remove the exposed photoresist, and whatever is not exposed, it will be not soluble. So exactly the same process used to happen in the old photography. In the film cameras, where we used to put a film and then click a photograph, you take the camera picture, the film is essentially a photosensitive material, something containing bromine and things like that. And then you take the photosensitive material, put it in the camera and then click. You're exposing light. Wherever you expose light, the photosensitive material becomes dissolvable. Okay, so you go into a dark room, put it in a solution and then you remove the regions which are exposed. So you get a negative. Okay, wherever light was, you get a negative, and then you basically use that to print images, photos. That's what used to happen in the olden days. So exactly same thing we can do here. So now wherever I expose my photoresist, I have this region which is completely exposed here. And then this is basically, when I develop it, I put it in a liquid solution, I remove that and I have this sort of a structure. Now what should I do? Once I have exposed, now you have the copper film and some pattern written. And this pattern, basically wherever I don't want my copper film to be there, I have exposed it. Okay. So now etch the exposed copper film. How do I etch my exposed copper film? For example, in this case, I can put it in a ferric chloride solution. If I put in a ferric chloride solution, the ferric chloride will interact with copper and then it will dissolve. We have seen that, right? Whenever, for example, this you can do even, in a very crude way in your home. Take a, let's say you have certain paint, okay? Think of a painted OHP or transparency or something like that. Some areas you want it to remain and some areas you don't want. Maybe you can put a mask, something like, if it's a solid thing, you can actually put a tape or something. Those regions you can block. Other regions you can put it in a liquid, dissolve it. So you get a very crude lithography system, right? Same thing you have to do here. So you are basically removing the etching. The only thing we have to make sure is the etchant, which is a ferric chloride in this case, does not dissolve the photoresist. If it dissolves the photoresist, everything is gone. Everything will be dissolved. So we just have to carefully choose. This is a chemistry which is very well optimized. So you can do that. And then finally you are left with a substrate with a copper film wherever you want it. And that is the split ring resonator here. What you're seeing, the split ring resonators are all simply exposed. Areas are etched. So you have this whitish region, which is basically the substrate. And the copper film is basically wherever you see this. Okay. So this is done over a large area and you can print it. So this entire process is called as photolithography followed by an etching system. Okay. Photolithography process is a very critical process here. All right. For example, what if I don't want to dissolve? I want to protect some areas. I don't want to dissolve. What can I do? Okay. So basically what happens is there are two types of photoresist. Okay. In this case, I want to, wherever I expose, I want to dissolve it. But many times I also want to have a scenario wherein I want the opposite. For example, I have what is called as positive photoresist, positive PR, which is essentially exposed regions dissolve. Okay, but sometimes we want a negative photoresist, negative PR, exposed regions become hard. Okay, so if you I mean, you can have that, because a negative photoresist will be opposite. In a positive photoresist, I said it's a long chain molecule with, if you shine UV photons, it will break the chains. But you can also have a scenario where you have the short chains and you cause light, and then you can make the cross-linking happen. The cross-linking happens and it becomes hard to resolve. Okay, those are called negative photoresists. The prominent examples are SU8, HSQ, and so on. A positive PR will be PMMA, and there are so many other AZ14, 1500 resists, and so on. There's so many of them. All right. So this is a standard lithography fabrication for PCBs, and I mean, there can be variants of how this is done, but yeah, this is something that can easily be achieved. Well, the question is, can you use positive as a negative photoresist? Yes. Huh. Okay, that's an interesting question. When do we need, let's say, I would just paraphrase you slightly, and I will say, can we use, when positive resist is clear here, we expose and then we are developing. What is the scenario for using negative photoresist? Okay, so one example could be, because let's say you want to fabricate the same split ring resonators like this. So this is my split ring resonator, right? So I want to etch everywhere else, and in this case I showed you the mask. The mask, again, you have to fabricate the mask and you have to worry about how to fabricate the mask and all that. So it becomes one more extra step. Instead, we can also use what is known as direct laser writing. Okay, a direct laser writing means, let's say I have my substrate like this, big substrate. Everywhere else my photoresist is there. I want to etch, basically in this picture here, I want to etch everything here. For example, if I take black here, so all of this region has to be etched. If I take a positive photoresist, right? Because I want to only protect my split ring resonators, which are a very small part of the entire structure. If I want to do that, I'll take a very long time to write it, right? Because exposed region, this is the actual region which I don't want to develop, or where I don't want to dissolve, is very, very small, maybe 10% of the sample. Remaining 90% of the area I want it to dissolve so that it can etch. So if I start writing it, it will take a long time for me to actually write it. Okay, so I cannot really use a positive, it takes long time to do a positive photoresist. Instead, if I have a negative photoresist, what I'll do is I'll simply, for example, in the same scenario, I'll have the copper film, and then I'll take this blue region in my structure like this, and I simply expose it to negative, put negative photoresist and expose only small area, 10% of the area. It becomes hard. Everything else will dissolve and I can easily etch. So that is one way of, where a negative photoresist could be useful. Another scenario is, I can even have, in this previous case, I have light which is transmitting wherever I want it to dissolve. I can have a reverse scenario. Wherever I want it to stay, I can make it blocked. Right? In the black region, the chrome can be there only where I want it to be there, right? And then everywhere else I am exposing, I can dissolve. So there are multiple variants of doing this. So in general, for the purposes of flexibility of nanofabrication, it's useful to have both negative and positive photoresist. A positive photoresist essentially dissolves when you expose. Negative photoresist becomes hard when you expose. Okay. Of course, there's a lot more details. People spend PhDs. So there's a lot of details, but at an entry level, I think this is sufficient for us. All right. So when you said that, this basically is step E, right, where you are exposing copper film, when you put it in ferric chloride, will not the ferric chloride go under the copper, under the mask, right, under the PR? Well, it will go. The only thing is, that's why it becomes again another important, okay. So what happens is, so I'm glad, we have these questions, because this is, there's a lot of details into this process. So now let's say you have this copper film on top, you're trying to etch, and you have this mask which is protecting. Now, the question is, because we are using ferric chloride, which is a liquid, you can definitely have a scenario wherein the liquid is going underneath and etching copper like this. You can have what is called as undercut. Okay, undercut. Because you can't force the liquid only to go where exactly the mask is. It's going to undercut, right? I mean, that's what we have seen many times. We see that. So this undercutting is important when you go to nanostructures. If you have millimeter scale, I think it's okay. What I can simply do is, instead of exactly taking my dimensions, I'll take a mask which is slightly of a different dimension. Suppose if I want to, because I know that, let's say I want to etch 200 nanometer film. I know it will take about 2 minutes or something. If I dip it into 2 minutes of ferric chloride, I can know. So, and I know the undercut is about 200 nanometers. Maximum it can be that, no? Because if I'm etching this film, which is 200 nanometers, the maximum undercut that can happen is 200 nanometers. Right? So now what I'll do is my mask, I'll reduce the dimensions or change the dimensions. So in that case, I'll make a mask which is slightly of this dimension. So even with undercut, I'll get what I want. So you see, I mean, I think this technology, right? Fabrication technology is one of the magic that has happened. It's one of the most complex industrial processes that we see. We take it for granted when we see all our chips that, they are working well, billions of transistors. There's a lot of detail to it and people have spent a lot of time trying to optimize it. So some of the state-of-the-art fabrication facilities are so advanced that, it takes, to set them up, the current state of art will take about $8 to $12 billion of money. It's one of the greatest scientific miracles that you can see. It's an amazing system. A lot of questions have to be answered. Of course, when we get into details, I think there are a lot of details. Yes. Okay. Anything else? All right. So this is basically the overview of how a fabrication can happen. Right. Now the challenge is, how do we make it small? Millimeters, it works. But we saw that, millimeters, you can only do finite number of things. We have seen split ring resonators in even micron scale. How do you fabricate those micron scale? Okay. So there are a couple of things that are very important in this process, because we want to make smaller and smaller features. And I want to basically in the next, this lecture, I want to tie it up to the traditional optics and whatever we understood in nanophotonics. I want to show you how to apply nanophotonic principles. So one of the things is, if you try to make some very, very small structures, we know that diffraction happens, right? If you make a small slit, take a small slit and then pass light through it, it diffracts. We have already seen that the diffraction basically gives you the fundamental order and then the higher diffraction orders which are coming out like this. Now, is that desirable or undesirable? This diffraction. The diffraction is desirable? Undesirable. Why is the diffraction undesirable? Right. So let's say if I have a structure which I want to print a line like this, okay, which is of this size. If I have diffraction happening, my size might become something bigger, right? We don't get whatever we expect. You might say, okay, I'll make it smaller, right? If it's diffracting, I'll make my slit smaller, just like the previous case I said. If I make it smaller, it diffracts more. So the problem becomes even worse. So we have to come up with new ways of actually understanding diffraction, right? And that is what I'm talking about here. Let's say you have a structure, let's say there is some mask which has some hole in it, which is basically a small slit like this, and you're passing light. Okay. So wherever the mask is, the metal is present, you can't pass light. Only through the small hole, the light will pass, and you have this diffraction. Now, the important feature to note is that these diffraction orders are what we call as spatial frequencies. In the first week, we introduced the idea of spatial frequencies, right? So wherein these diffraction orders are spatial frequencies, right? So now what's happening is, we saw that the lower spatial frequencies catch the broad contour of the surface. The higher spatial frequencies define the sharpness. So if you have, if somehow you manage to capture all the diffraction frequencies, you will get a square. I mean, in this case, it should be a slit, but essentially you get this main feature. Okay. But suppose if you have only some diffraction orders, right? For example, m equal to 1, 3, 5, so on. If you capture only some of them, you will see that the pattern becomes like a sine wave. If you only take the 0th order, you get a sine wave. But if you take the higher diffraction order, slowly you'll start seeing that the pattern becomes square. I mean, this is something very simple we can do in even Fourier transforms, right? You take a sine wave, you plot it, you start putting harmonics, okay, odd harmonics of the sine wave, you start seeing that it becomes a square wave. Of course, we have to adjust the amplitudes of it by the whatever the Fourier coefficients we know from the theory. If we do that, we get a square wave, right? Similarly here, if I want to print a pattern of this size, I have to capture all the diffraction orders if possible. But the problem is, let's say if I have a lens like this, I'm going to capture some diffraction orders. Very high diffraction orders I'll miss because they're at very high angles. My optical system cannot capture them, right? What happens if I miss these diffraction orders? My pattern becomes broader. I lose resolution. Okay, that is a fundamental problem. Okay, now how can I overcome that? That's a challenge, right? How do we overcome this? Well, in optical systems, there's only something you can do. And this is again tying back to the original discussion in the first week, where we talked about the resolution, right? I said this is going to be useful. Nanophotonics ideas are useful because one of the ways to improve the resolution will be use a shorter wavelength. If you use a shorter wavelength, it's not going to undergo as much diffraction. Okay, the diffraction limit is basically lambda by 2, we said. So if you use a shorter wavelength, you can overcome that. Or you can actually use the higher NA objective. For example, here, the objective had NA of let's say 0.5, 0.6 something. If you use a higher NA, that means you can capture more of this light. Numerical aperture is simply the amount of light gathering capability of a lens. If I have a higher numerical aperture lens, I can capture larger number of diffraction orders, so I can improve the resolution. So if a high NA, again the resolution will be better. Or there is this K1 parameter which we talked about, which is basically an empirical parameter which captures the process, I mean the system and so on, so many other things. Let's not get into what K1 parameter is, but in effect we have lambda and NA, which are the two parameters. So we have seen this already. If you go to extreme UV, you can get very good image. If you go to, krypton fluoride, which is 248 nanometers, you get very poor image. Alright. So now we have to use lower wavelengths. But in technology, it's been a challenge to go below 193 nanometers. The current lithography technology is 193 nanometers. And in exploratory regimes, nowadays in very advanced, the most recent couple of years, they're using what is known as extreme UV, which is 13 nanometers. But it turns out that this is not a very efficient process. We have seen recently, there are some news coming out of Taiwan saying that these extreme UV photolithography machines are consuming so much of power. The power, the bills, right, for TSMC are increasing by 30% or so because of this UV. So they are very, very power hungry. They are not at all reliable. So there are a lot of issues with that. I mean, they even projected that the one single company, TSMC, can consume up to 10% of the power consumed in Taiwan. It's a lot of power that's being consumed because, UV is a challenge. Anyway, for us technically, yeah, UV is a way to go, right? So is there anything else we can do? Because UV is not easy. Okay. Since we understand now a lot of things about photonics, we can understand some of these techniques that are being applied. Because I told you that in the current generation, we are fabricating chips of the size of 10 nanometers, right? So how can we fabricate that with 193 nanometer lithography? The diffraction limit is going to be simply lambda by 2, right? So roughly about 95 nanometers. These are the smallest features we should be able to print. How are we going to 10 nanometers? That is really where some of the magic that happens in the semiconductor industry can be seen. So I'll give you a couple of examples to highlight how photonics is helpful. So one of the cases is basically the optical proximity correction. Okay. So think about a mask. Okay. Now my mask has a feature of this. There is a square and then there's a L-shaped object like this. There are two shapes. Okay. Let's assume that they are very, very small. And so what happens when you transmit that? When you shine light, you can transfer this pattern. Okay. If you have a negative mask, negative resist, you will get a hard resist region like this, because wherever light has gone through, it will become hard. Now, if there is diffraction, what will happen? You lose some of the higher spatial frequencies. That means the edges become very smooth. When the edges are smooth, that is not desirable. Okay, how can I correct that? I can correct it by intelligently calculating what my diffraction pattern is. Diffraction is a very well understood phenomena. Given a slit, I can calculate what my diffraction pattern is. So if I have such a scenario, I can compute what my pattern is going to be and then modify my mask. So instead of taking a standard mask like this, I will try to take a corrected mask, which has this additional, pecks on the sides and so on, which are this additional distortion that we are introducing in the mask, so that when it gets diffracted, you get the correct image you want. So what is happening? These sharp edges are getting lost, right? So I'll try to make them larger so that more light passes through that and I get my image exactly what I desire. So this process is known as optical proximity correction. I can try to avoid some of the small details which are close to the edges, okay? And there are there are some more things we can do anyway. So, and the image on the right is basically an SEM image of an OPC mask. Okay, you see these OPC features, proximity corrections. These features will actually help to print the right size shape, okay? And if you look at it, this is 1 micron. I think the scale bar here is 1 micron. So these features are like 1 micron. If you try to print them with a optical photolithography system, you cannot. So to even make a mask is a challenge. Okay, we'll come to that. All right. So any questions here? Okay. All right. So so there are even other techniques available. So we said that, let's say we have a mask, okay? Again, another type of mask is something like this, okay? Wherein you have this chrome which has features like this. So basically you have these two windows where light can transmit, all right? When you have such a scenario, we know that each of them, diffracts to some extent and you have some broadening happening. So each slit will actually give you a pattern like this, and overall you'll get a pattern which is like this on the wafer. So what is happening is you are not able to resolve these two features which are very close to each other. If they are very far apart, no problem. There will be individual profiles, no problem. But if they are very, very close, nanoscale dimensions, then the diffraction will happen and give you a broad intensity profile like this, which is not desirable. So what can we do to avoid that? One of the interesting ideas that people have proposed is I'll introduce a phase shift in one of the structures, adjacent structures. For example, I have two structures here. In one of them, I'll introduce a phase shift. How do I introduce a phase shift? How to introduce phase shift? How to do that? We know that whenever light travels to through a material, it undergoes a phase lag, right? So if it travels to vacuum, what is the distance over which it acquires a phase of 2 pi? The lambda, right? So basically a 2 pi phase means it goes through one cycle. One cycle, the distance over which it goes through one cycle is basically the lambda. Now, if I put let's say in this case, a glass piece on top, what should be my thickness of the glass piece so that it gets a phase of 180? What thickness of glass will give phase shift of 180 degrees? So if you have glass, there is a certain wavelength which is propagating in glass. So the wavelength in glass will be how much? Lambda by n, right? The wavelength in glass is going to be lambda g, or lambda glass is going to be lambda by n. N is 1.5. The free space wavelength, let's say, is 365 nanometers. Divided by 1.5 will give you some number, okay, 200 something, okay? That is the wavelength in the glass. We have already computed this in some of the assignments as well. So once you have the wavelength, what is the distance over which you get a 2 pi phase shift? That particular wavelength in the glass. Now, how much will be the phase shift, distance to get phase shift of 180? You have to do lambda by 2. So the lambda in glass is, let's say, 200 nanometers. I should put 100 nanometer film. If I put 100 nanometer film, I get a phase lag of 180. What is the use of that? Well, it turns out that you have amplitude now, which is, there are two peaks which are out of phase. Okay, and when an interference happens between these out of phase films, you will see that interference and amplitude, if you take, basically you get two peaks which are very, very nicely resolved. Just by introducing phase shift, I am able to resolve the patterns which I could not resolve originally. They basically are destructively interfering in the center here. The phase shift is causing them to destructively interfere in the center, and you get good resolution. So this is one more way of trying to improve the resolution optically. So even though you have the traditional diffraction limit, industry uses a lot of these kind of ideas, right? So you can, this is one more technique that people use, again, optical technique, right? This is one more technique for resolution enhancement. How do we deposit that? So how do we deposit this additional film? It's difficult. Again, you have to do lithography. Traditionally, much more simpler technique is basically how to, you etch away some part. For example, you had a mask. Now you keep a certain thickness of quartz. Let's say this is made of quartz, right? If you have a certain thickness, you have some phase shift. In another region, you just simply etch it away a little bit. If you etch away, the thickness has reduced, so you can actually get phase shift. You can add a phase of 180 or actually reduce it. It doesn't really matter. You get the same effects. Okay. So now again, I mean, this is, you want an etch depth. What should be the etch depth to get a phase shift of 180? You can compute that. I mean, basically lambda by 2 is the 180 means I want lambda by 2, and refractive index in that medium, glass is 1.56 minus 1, air is this much. So that will give 132 nanometers. So you get basically in 172 nanometers etch depth, you can get these two beams which are out of phase, 180 degrees out of phase. Alright. How do we do this? Well, what we can do is, you have, let's say, quartz substrate, you have chrome which is coated all over there, and in one place I want to have etching. Okay. So if I put a mask and then I cover all of it and then etch it only in some place. Okay. Now the question is, these features are very small. Why not undercut? Okay. That's a challenge, right? So again, so there are various etching tools. One, ferric chloride we talked about was actually called as wet etching. You have a liquid which is going in, but in addition to that, we can actually employ what are known as dry etching techniques, which actually have basically gases. You have a gas under low pressure, and then you essentially make sure that atoms, the etchant atoms, go only vertically. By doing some tricks with that, you can actually etch vertical structures like this with minimal amount of undercut or more anisotropy. All right. So this is about dry etching, and you can create a face mask like this. All right. So a lot of optical techniques can be applied. All right.